Anti-reversion steps are a specialized feature incorporated near the engine's valve to enhance performance. Their primary purpose is to prevent exhaust gases from flowing back into the combustion chamber during valve overlap. By minimizing this unwanted reversion, these steps help improve engine efficiency and power output. This advanced technique is particularly beneficial in high-performance engine builds where precise control of airflow is crucial. Ultimately, anti-reversion steps contribute to cleaner combustion and more consistent engine operation. Reversion in engine airflow refers to the backward flow of air or fuel mixture from the combustion chamber back into the intake system. This phenomenon is typically caused by valve timing overlap, where both the intake and exhaust valves are open simultaneously, allowing exhaust gases to travel backward. Reversion can lead to a loss of engine efficiency, reduced power output, and poor throttle response. The impact of reversion varies across engine configurations, with high-performance or aggressively cammed engines being more susceptible due to their extended valve overlap. Understanding and managing reversion is crucial for optimizing engine performance and ensuring smooth operation. Traditional methods to combat reversion, such as chemical inhibitors and mechanical interventions, have long been used to address this persistent issue. While these approaches can offer temporary relief, they often fall short in providing lasting solutions. Many conventional techniques require frequent maintenance or introduce additional complexities to the process. As a result, industries continue to seek more effective and sustainable alternatives. This ongoing challenge highlights the need for advanced solutions that can overcome the limitations of traditional methods. Adding subtle anti-reversion steps near the valve is a technique used to improve airflow dynamics within an engine. These steps are designed to minimize the backward flow of gases, known as reversion, which can disrupt engine efficiency and performance. Precision in implementing these steps is crucial, as even minor inaccuracies can negate their intended effects or introduce new inefficiencies. By carefully controlling the shape and placement of these features, engineers can enhance combustion stability and overall engine output. The effectiveness of this approach relies on meticulous attention to detail and a thorough understanding of airflow behavior. Anti-reversion steps are most beneficial in high-performance engine builds where exhaust flow dynamics play a critical role. These techniques are often considered for engines with aggressive cam profiles, high RPM operation, or forced induction setups. In such scenarios, anti-reversion steps can help reduce the backflow of exhaust gases into the combustion chamber, improving overall efficiency and power output. For street-driven vehicles with mild modifications, the benefits may be less noticeable, but in racing or heavily tuned applications, the gains can be significant. Careful assessment of your engine's specific needs and goals will determine whether implementing anti-reversion steps is worthwhile. Small Burr modifications are based on the principle that even minor adjustments to the shape and surface of engine components can have a significant impact on airflow dynamics. By carefully smoothing or reshaping burrs, tiny imperfections or protrusions, engineers can create a more streamlined path for air and fuel mixtures. This reduces turbulence and helps maintain a steady flow, which is crucial for efficient combustion. Additionally, these subtle changes can minimize reversion, a phenomenon where exhaust gases flow back into the intake, disrupting performance. Through precise modifications, the overall efficiency and responsiveness of the engine can be improved. Begin by selecting a small burr, which allows for greater precision when working near the valve. Gently position the burr at the targeted area, ensuring your grip is steady and your movements are controlled. Gradually create the anti-reversion steps, making subtle adjustments as needed to maintain accuracy and avoid removing excess material. Throughout the process, focus on smooth, deliberate motions to achieve clean and consistent results. This careful approach helps preserve the integrity of the surrounding surfaces while effectively shaping the anti-reversion features. Choosing the correct burr size and shape is essential for achieving precise and efficient results. The burr should match the valve's dimensions and the desired finish, with finer burrs providing smoother surfaces and coarser ones removing material more quickly. To maintain consistency across multiple valves, use the same burr specifications and settings for each job. Regularly inspect and replace worn burrs to ensure uniform performance. Consistent technique and careful equipment maintenance are key to optimal outcomes. Begin by carefully examining the modified area for any signs of irregularities or unintended obstructions. Use precise measuring tools to check the dimensions and confirm that the passage remains consistent with the original specifications. Pay close attention to the smoothness of the surfaces and the alignment of components, as even minor deviations can impact flow. It's important to verify that the modifications have not introduced any new restrictions or bottlenecks. Document your findings thoroughly to ensure the effectiveness of the changes and maintain optimal performance. When incorporating anti-reversion steps, it's important to be aware of several common pitfalls. One frequent mistake is applying excessive force or using incompatible materials, which can compromise the effectiveness of the solution. Overlooking precise measurements or skipping manufacturer guidelines often leads to improper installation and recurring issues. If problems arise, double-check alignment, ensure all components are securely fastened, and consult technical documentation for specific troubleshooting steps. Taking a methodical approach helps prevent errors and ensures long-term reliability. Several engine builds have demonstrated remarkable improvements after applying this technique. For instance, a standard V8 engine saw its horsepower increase by 15%, with a noticeable boost in torque across the RPM range. Another example involved a turbocharged four-cylinder, where fuel efficiency improved while maintaining higher peak power. In each case, the engines not only delivered better performance metrics, but also exhibited smoother operation and enhanced reliability. These real-world results underscore the tangible benefits of incorporating this approach into engine tuning and modification. In summary, anti-reversion steps near the valve are most effective when aiming to reduce unwanted airflow reversal, which can improve engine efficiency and performance. These steps are particularly useful in high-performance applications, where precise control over airflow is critical. Understanding when and why to implement such modifications requires a deep knowledge of engine dynamics. Precision in every aspect of advanced engine work is essential, as even small adjustments can have significant impacts on overall performance and reliability.